In section 14.4, we've already talked about mass and center of mass, including the moments with respect to the x and y axis. Now we're going to be looking at moments of inertia. Mass is a measure of the tendency of matter to resist a change in a straight line motion. The moment of inertia is about a line, is a measure of the tendency of matter to resist a change in rotational motion. For example, if a particle of mass m is a distance d from a fixed line, its moment of inertia about the line is defined as I equals md squared, where m is the mass and d is the distance. So our mass times our distance squared is the moment of inertia. When the mass is calculated with a double integral with variable density, we can determine the double integrals that will give us the moment of inertia about the x and the y-axis. The moment of inertia with respect to the x-axis is a double integral r, where the distance from the x-axis is y. We square that distance and multiply by the mass, which is your density of x in terms of x and y times your differential area. And we can also look at the moment of inertia with respect to the y-axis, or about the y-axis, and that's a double integral over a region where the distance from the y-axis is x, and we square that and multiply the mass, which is our density times area. The sum of the moments I sub x and I sub y is called the polar moment of inertia, and it's denoted by I sub O. In this example, we want to find the moment of inertia about the x-axis of the lamina in this example. Okay, the example we did in the previous PowerPoint here is where the density was k times y, and the region is bounded. The region was bounded by these functions. So to find the moment of inertia about the x-axis, it's the distance from the x-axis, which is y squared, times your density, which is k times y, times the differential area, which is dy dx. You would integrate the inside first with respect to y, substitute in the bounds, and then you end up with a single integral that you can evaluate. That k is a constant. You can bring that out in front. And this ends up being y squared times y, which is y to the third. When you integrate it, you get y to the fourth over 4, so you can bring the k and the dividing by 4 out in front. When you substitute that back in, and then you evaluate this integral from -2 to 2, and simplify the result, you get the moment of inertia about the x-axis is 32,768 k divided by 315. The moment of inertia I of a revolving lamina can be used to measure its kinetic energy. For example, suppose a planar lamina is revolving about a line with an angular speed of omega radians per second, as shown in this figure. Then the kinetic energy E of the revolving lamina is found by this equation. And the kinetic energy E of a mass moving in a straight line at a velocity v is given using this equation. So we have two equations, one kinetic energy for rotational motion and kinetic energy for linear motion. So the kinetic energy of a mass moving in a straight line is proportional to its mass, but the kinetic energy of a mass revolving about an axis is proportional to its moment of inertia. Some other applications we are going to look at is the radius of gyration. We have that r double bar of a revolving mass m with moment of inertia I is defined as this. R double bar is equal to the square root of I, that's your moment of inertia, divided by the mass. If the entire mass were located at a distance r double prime from its axis of revolution, it would have the same moment of inertia and consequently the same kinetic energy. For example, the radius of gyration of the lamina in example 4 about the x-axis is given by this y double bar, which is equal to the square root of the moment of inertia about the x-axis divided by the mass, And then when you simplify that, you get approximately 2.469.